Hi everyone, this lecture is going to be on section 4.5 in Thomson. The section is called covariant form of the Dirac equation. So, when I first saw this, I was like, why are we doing this? Oh, and then I saw these gamma matrices. Now I know why we're doing this. So, just to remind everyone what covariant and contravariants are. Remember when we did these, got introduced to the four momentum vectors, right? P mu, right? Where the first component is energy, the other three components is the three momentum, the three spatial momentum, right? This is known as a contravariant. We can even write that out for momentum, okay? But when we want to do a dot product to get a Lorentz invariant, what we do is we actually dot this with the covariant. And one way you can think about this is that contravariant varies one way when you do a Lorentz transformation, and covariant varies the opposite direction in a Lorentz transformation. Therefore, the product between the two is actually a Lorentz invariant. Okay, and to convert from the contravariant to the covariant, what you're doing, at least in the convention of this class or this textbook, is that we're going to negate all the spatial components. Okay. So we're going to do a similar thing with the Dirac equation. The Dirac equation, remember, is from basically acting, I should have wrote this out, right, where if you have the Schrodinger equation, okay, the time derivative, right, how the partial by partial t of a particular state is equal to whatever that Hamiltonian is acting on that state. In this case, we're going to be acting with the Dirac Hamiltonian. And the Dirac Hamiltonian is this dot products of a bunch of alpha matrices, and these are 4x4 matrices, dot producted with the, so just to remind you, these are 4x4 matrices, and each part of this actually has three components, right? Alpha x in the x hat direction, alpha y in the y hat direction, and then alpha z in the z hat direction. And this gets dotted with into the momentum, and then you also have the mass term, which has this beta 4x4 matrix attached to it also. Okay, so if you were to plug this Hamiltonian into the Schrodinger equation, what you'll find is that, well, there's this time derivative term, just like in any of the Schrodinger equation. But then this dot product here, right, basically turns into this negative I alpha x partial by partial x minus I alpha y partial by partial y, and then similarly for the z. And then, of course, you still have this mass term, all of these matrices acting on this wave function. And since these matrices are 4x4, right, each of these are 4x4 matrices, this forces the wave function to be a row vector. Actually, it's called column vector, right, of four components, psi 3, psi 4, right? Okay, and this is where we come up with the spinners that we have to deal with now. Okay, so I'm going to rearrange things before we get started in this section so that it looks in the same order as what we're going to see in equation 4.31. What I'm going to do is I'm going to set this whole thing equal to 0 by moving everything to the right hand side and then flipping everything, moving everything to the left hand side and then setting everything to 0. Okay, in fact, what I'm going to do is I'm going to write it in the same order as here. Okay, I'm going to move all of this to the left hand side. Okay, all the alphas, okay, I alpha x partial by partial x plus I alpha alpha y partial by partial y plus I alpha z alpha partial by partial z. Okay, and then the next term I'm going to put is the time derivative. So since these became positive, I'm moving everything to the left hand side, so this time derivative is still positive, but then this beta, right, since is positive here, when I move it to the right hand side, left hand side, is going to become negative. Okay, all of this is acting on the wave function. It's going to be all equal to 0 because I moved everything to the left hand side. Okay, so the first thing we're going to do is we're going to multiply this whole thing by beta. Okay, just overall beta. Okay, so multiplying this entire equation by beta the first one is going to pick up a beta times alpha x, right? The book actually even factor in, right? Multiply this in, oops, so this wave function doesn't belong here. Okay, multiply this, the wave function into each of the terms to see it explicitly. But, you know, you have beta times alpha x, beta times alpha y, beta times alpha z. Okay, and then the time one doesn't have an alpha matrix attached to it, so we just only have the regular beta. Okay, and then the mass term has a beta already, so we get beta squared instead. Okay, so hopefully all of this makes sense. Okay, so looking at this, okay, what we're going to do is we're going to throw away these betas and alpha matrices and yet define a new set of matrices called gamma matrices. These are actually matrices I remember when I took this class 18 years ago. Okay, so we're going to define gamma matrices as basically the same way we define a 4 vector, where we start with the index 0. Okay, gamma 0 is just beta without having to multiply by anything. Okay, gamma 1 is beta times alpha x, and then beta 2, sorry, I keep saying beta. Gamma 1 is beta times alpha x. Gamma 2 is beta times alpha y. Gamma 3 is beta times alpha z. Okay, so hopefully these indices make sense, because I mean, typically you would think about this as like the time component, and these are the 3 spatial components, right? X, Y, Z. Okay. What happened is that, well, when you see this, right, so let's say we look at the time term, which is here, right? Beta is the same thing as gamma 0, so this term comes down here. Let me just highlight those, right, in green. Okay. Okay, and then, right, let's do at least one of the spatial components. So let's do gamma 1, right? Gamma 1 is beta times alpha x, so it comes down here the same way as up here, right, without the wave function part. Well, let's just highlight the whole term. Okay, and then the mass term, well, and similarly with the y and the z, so hopefully we don't have to go through that. But, right, beta square, right, what the heck is beta square? Beta square, remember that beta, at least in the Dirac Pauli representation, right, and this is actually true in any representation, but just so we can see it explicitly, what is beta square? Okay, beta square is I, negative I, right? Regular beta is just the identity matrix, but then the negative version of that on the lower 2 by 2 part, right? These are 2 by 2 matrices. Okay. When you multiply these together, what do we get? Right? Right, we get the identity matrix still on top, I times I, right? And then you do all these row vector stuff, right? But then you have 2 negative identity matrix, which combines to give you just the regular identity matrix. So this is actually just the identity matrix, the 4x4 versions, and therefore is actually not written here. So just be careful, right? Just because this says M, it doesn't mean it's a number, okay? It's actually the identity matrix, a 4x4 identity matrix times that mass, okay? So just be a little careful there, okay? What this does is that it compactifies this equation, right, by defining these gamma matrices as, you can probably foreseen this, right, as just gamma mu, right, where gamma mu are these 4 of these matrices with index 0 to 3, just like what we were keeping track of, you know, form momentum and other covariants like that. Okay. In chapter 2, we also learn about this thing called covariant derivative, right, where a covariant derivative, right, with the index downstairs, right, is going to be whatever the time derivative is, and then the 3 spatial derivative with each of their respective components in the 4 vector. Okay, so let me write this out a little bit more explicitly, because, right, the book just kind of skip to this, right? So looking at this equation up here, right, you have negative I, gamma 0, partial by partial t. I'm going to factor out this psi once again, because I think it's actually easier to see if we have that separate. Okay, gamma's 1, partial by partial x, plus I gamma 2, partial by partial y plus I gamma 3 partial by partial z. Okay, and all of this is minus m, all acting on our wave function psi equal to 0. Okay, now with the combination of gamma mu and then the covariant derivative, partial mu, okay, where's these three things, right? So this, I'm going to do my highlighter trick again, right? This piece, this blue piece, right, is this part and this part together, right? And then let's do one of the spatial component, partial by partial x, gamma 1 is this part with this part together, right, with an I in front. What you can do then is that with these two shorthand, well, these definition, right, what you can do is that this whole thing in front part just becomes gamma mu, okay, with this dot product, right, just like what we did with the 4 momentum dot product up top, right? You have one index upstairs, you have one index downstairs, okay? In the Einstein summation notation, this is just, you know, gamma 0 plus partial 0, gamma 1 plus gamma 1 plus partial 1, you know, in this case partial x, okay? And then so on with the y and the z component also, okay? Of course, you still have this mass term, okay? So we have to write that in. I also forgot the I in front, right? Because these gammas and partial derivatives don't include that I, right? And all of this, right, is going to be acting on your wave function is going to be equal to 0, and this is the covariant form of the Dirac equation, which is exactly what the title of this section is. Okay, right? So why is this a covariant form, not a Lorentz invariant form? Okay, what I'm going to ask you to do is think about this a little bit for a couple of minutes. Okay, so please pause the video, and then I'm going to keep talking, because if you don't pause, I'm just going to give the answer away. Okay, so pause if you don't want the answer. Okay. Okay, so I'm going to tell you why this is a covariant form, not a Lorentz invariant form, even though it looks like there's a dot product between here, right? These gamma matrices are not variables, right? The gamma matrices are not variables, okay? So when you do a Lorentz transformation of a constant, that is still the same constant, so you don't change things. So this is actually not a contravariant, right, matrix. Okay, okay, and you have that not contravariant thing, right, multiplied by covariant thing. The derivatives are covariant, so therefore the whole thing only remains covariant. It does not change to a Lorentz invariant. Okay. Okay. So writing these gamma matrices out. Okay. So gamma 0, as I already showed you, is basically the beta matrix, right? So this is actually nice that the book actually printed out the 4x4 version of this, as opposed to just writing the 2x2 buried inside a 2x2 version. Okay. So gamma 0 is just the identity matrix with the latter two pieces with a negative sign. Gamma 1 is basically going to be a bunch of sigma x's. So that's probably why they write it this way, because I don't remember this, but I always remember that it's just the off-diagonal sigma polymatrices. Okay. Sure, there's a negative sign here also. Okay. And then gamma 2, gamma 3 are the respective, you know, sigma y, negative sigma y, right? And this one is sigma z, negative sigma z, right? That's what these gamma matrices are. Oops, no, they're not, sorry. It's beta times that, right? That's what gamma 3 is, right? There's these beta multiplied by it, so I should not be too cavalier about it. This is going to be beta times gamma 2 equals gamma 2. Okay, so this is nice that you have this, you know, in the book somewhere, so you can copy it out, because we're going to use these matrices a lot until we get to the end of QED in the next couple of chapters. Okay, so what we're going to talk about next is the adjoint spinor of these covariant current. Okay, so in the previous section, I think it was the two sections ago, I think in 4.3, right, we calculated what the current and the probability density of these direct spinors are, where the probability density is just psi dagger psi. It has to be a dagger in this case, right, because, right, these psi's are now 4 component wave functions known as spinors. Oops, 3 psi 4, right? And then the non-dagger version is the column vector 2 psi 3 psi 4, right? So when you do psi dagger psi, right, you get psi 1 square plus psi 2 square plus psi 3 square plus psi 4 square. Okay, and these are going to be inherently positive because you are taking the magnitude of basically some complex function. Okay, right, what we can do is combine these into a 4-vector form, just as we did with the Dirac equation, and we're going to see how that's going to be useful. We're going to define the covariant current, right, what's going to be up here. I think this should actually be called the contravariant current, but that's okay. As J mu, right, just as we did momentum, right, where we just put in something in the first component and then some spatial component here, right? And what makes sense here is that, well, we're going to put rho, right, just the density here, and then the current, right, which is psi dagger alpha times the wave psi. Okay, that's a 3-component spatial thing, so that's going to go in our spatial part of our 4 vectors. Okay, and if you actually write this out, what's going to happen is that you're going to see that it's going to be psi dagger gamma 0 times gamma mu, where mu is the index that goes from 0 to 4, 0 to 3, right, for the particular gamma matrices that we're dealing with. Okay, multiply into the 4-component spinor, Dirac spinors that we found to be necessary in order to solve the Dirac equation. So I'm going to show you some example because this is a little bit opaque for me also, right? So let's say for mu equals 0, okay? I want to figure out what J0 is, okay? So J0, I'm just going to copy the right-hand side here. It's going to be psi dagger gamma 0, right? This 0 doesn't have to do with has nothing to do with this other 0, is that we're changing this mu, right? This mu goes to 0, okay? And then we get psi over here. We should get this back, right? So what's gamma, right? Gamma, right? Go up here, looking at this, right? Gamma is, gamma 0 is just 1, 1, negative 1, negative 1 on the diagonal. Okay, I'm going to actually copy that down so I can remember it. A bunch of zeros. Okay, gamma 0 times gamma 0, so that's what we're trying to calculate. Okay, right, similar to the beta matrices. In fact, it is the beta matrices, right? Remember, gamma is the beta matrices, right? This just turns into the identity, right? Because these negative signs multiply each other to just make it a positive. Okay, and therefore this whole thing just collapsed to psi dagger psi as we want. Okay, I'm going to do one of the spatial one, and then you guys can do the other two in your homework. Okay, so let's say for mu equals to 1, so I'm trying to calculate what J1 is. Okay, J1, once again, I'm just going to write the definition on the right hand side here. Right, gamma 0, gamma 1, okay, and that's going to be acting on the wave function. Okay, right. So gamma 0, we're also going to have to deal with this gamma 0, gamma 1, 1, 1, -1, -1, 0, 0. And then gamma 1, right, is the Pauli matrix C in the X component, but it's in the off diagonal instead. Okay, so a bunch of zeros here, 1, 1, -1, -1. Okay, right. So if you were to do this multiplication, right, this first component actually gives you 0, right? It's not until you reach the let's see. I'm going to write all these zeros out so I can keep track of them. I think it's a good idea the first time out. There's a lot of zeros to write though, right? Trying to be quick, but then end up spending more time. Okay, so this part is 0. So unfortunately you can't see my hand, so what I'm multiplying is this row with this column, right? And since none of the index actually match, so 1 gets multiplied by 0, and then 0 gets multiplied by a bunch of zeros, and then -1, that still turned out to be 0. Okay, so I'm going to do this more explicitly since it's the first practice we have. Okay, and then the next iteration, what I'm going to do is I'm going to multiply this row with this same first column, so that'll determine what this number is. Okay, similarly, this turns out to be 0. Oops, wrong color. Okay. Okay. Similarly, this will turn out to be 0. Okay, but the last one, right, this one, these two negative signs actually run into each other. Okay, and that would actually give us a 1 here. Okay, all right. So let's see, and then I see how this matrix is going to turn out. Okay, so what's going to happen is that you're going to have 0, 0, 0, and then just 1s along the diagonal. Okay, 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 and this 1 against the diagonal is basically the Pauli spin matrices, right? Okay, and that's exactly what alpha x is going to be. Okay, right, and this will give you just basically psi dagger alpha x psi. Oops, the x is not upstairs. Okay. Okay, so that's how you do these multiplications. So in fact, I think I caught myself here where, right, these negative part of these gamma matrix C came from us multiplying by the beta, not from the definition of alphas. So sorry for that, where you have to correct your notes. Okay. All right, so you'll get to play around with these in the homework for mu equals to 2 and 3. Okay, so with this definition, we can rewrite this continuity equation. Remember the continuity equation that we found before was that how the probabilities changes over time plus the divergence of these probability current, where you have particle flowing out in some volume. Okay, those have to add up to 0, because any particles you lose, you're going to negatively affect the probability density inside that particular volume. Okay, so with this new definition, right, J up here, I'm going to copy that down, J mu, right, it is a lowercase unfortunately, so it's kind of funky writing, okay, where it is rho the J. Okay, so in this case, right, we have a time derivative here. Okay, and remember that the covariant derivative is partial by partial t, partial by partial x, partial by partial y, partial by partial z. Okay, okay, so that gives us this term here, right, the divergence of J, right, this divergence operator is basically partial by partial x plus partial by partial, there's a vector part of it, okay, that, plus partial by partial y, y hat, plus partial by partial z, z hat, and let's say this dotted into jx, x hat plus jy, y hat plus jz, z hat, right? So this dot product, right, what's going to happen is that you're going to have partial by partial x, j, x, right, partial by partial y, jy, plus partial by partial z, jz. Sorry to be kind of lingering on this, just want to be a little bit explicit here, right? So when you, so that's the equivalent of basically taking the covariant derivative of this, of both the contravariant form of the probability density squished together with the current. Okay, right? So if we, that makes sense. So when you have this, you can actually write this entire continuity equation by just writing partial the covariant derivative partial mu with the contravariant current j mu. Okay, and so looking at what this looks like, right? So remember j mu, I have it up here again, right? Are these gamma matrices, right, with the sandwich between these wave functions? What we can do is that we can even kind of skip this, shorthand this a little bit, okay, by writing what's known as the adjoint of the spinner. Okay, so right now this thing right here, right, is psi dagger. Okay, what we're going to do is we're going to even be a little bit lazier and define a new adjoint spinner. We're going to call that psi bar. Okay, so this, in this case, this does not mean the antiparticle. Okay, what this is going to be defined as is basically psi dagger gamma 0. We're just going to put these two things together and call it psi bar. Okay, so now this four vector current is not going to look like just j mu as usual before, but instead of having to deal with this gamma 0, okay, all we have to do now, right, is write psi bar gamma mu psi. Okay, so skipping that, basically replacing psi dagger gamma 0 with psi bar. Okay, and that's going to help us a lot with the notation in the future. Right, so I'm going to stop recording and hopefully get this right.